Okay, so this video is going to walk through quickly the reasoning behind why we require all of our quantum mechanical operators to be Hermitian. Okay, so remember that a Hermitian operator has a very specific definition, which is given by this equation here, where we have the integral of psi star times our operator times psi, okay, also known as our average value of quantity A. Okay, it's just your regular old average value expression. And then if we have our Hermitian operator, we know that that expression is equal to this quantity, where we've basically just taken the complex conjugate of that average value. So here we have now the integral of psi times the complex conjugate of the operator times the complex conjugate of the wave function. So in other words, we have the average value of A and taking the complex conjugate of that. So here, if we have a Hermitian operator, that's just telling us that the average value of our quantity A is equal to the complex conjugate of that average value. Okay, let's go through a few steps and see kind of how that situation arises. So, and why that's meaningful for us for our quantum mechanical purposes. Okay, so a couple things we know from our earlier conversations is that the quantity here, that A hat psi, is equal to, we know, our eigenvalue A times our wave function. So that's just our regular old eigenvalue equation that we've been using. And same for this quantity over here. So A star psi star is also going to result in an eigenvalue equation for us. So in that case, we would have an eigenvalue of A star psi star. Okay, so that's just applying our eigenvalue equation approach there. Okay, so we're just going to pop these results that we got here into our Hermitian operator situation. Okay, so just subbing in our eigenvalue results there, and when we do that, we end up with psi star A psi d tau equals the integral of psi A star psi star d tau. Okay, and now, just like every other integral evaluation, let's pull out our constants to simplify things for us a bit. So here we'll pull out the A. We're left with psi star psi d tau. And then same on this side, we'll pull out our A star. And we're left with psi star d tau. Okay. And then just one other kind of rearrangement here. So let's just bring this quantity over to our left-hand side. So let's just bring everything over to the left-hand side so that we can set our expression equal to 0. So if we do that, we end up with this expression where we know that that equals 0. Okay, so far so good. So one thing we want to take note of here is that, hey, we know something about these expressions, right? We know that they're equivalent to each other. So it doesn't matter if we write psi star psi or psi star. Okay, there's nothing in there like an operator or anything that's getting in our way anymore. Right, we've already evaluated that. So these are essentially equivalent integrals. Okay, so we're just going to group those together, and then we'll factor out our constant coefficients. So again, just one more little simplification here. So we can rewrite that as a minus a star times the integral of psi star psi. Okay, so now we know something about this integral. Okay, so remember, this is essentially just our probability distribution, right? So this is how we calculate our probabilities for a given interval. Okay, now I haven't included any intervals on these expressions. We'll just assume their overall space for whatever your system is. Okay, so negative infinity to infinity, or 0 to a, or whatever your limits may be. Okay, so we know that the probability distribution, this guy is always going to be positive no matter what, right? So we basically are taking the square of our wave function. We know that the square of a quantity has to be positive, right? Or it could be 0, right? But it's only 0 if your function is equal to 0 everywhere. Okay, so our only other option is 0, and that's only if your, oops, let me use my same notation here, only if our function is 0 everywhere. Okay, so if that integral is only 0, if our wave function is 0 everywhere, then that means it's only 0 when we don't have a particle, right? So remember, if the wave function is 0, that means there's no particle anywhere, and that is not the most interesting question for us to be spending our time on. So we don't pay attention to those situations. Okay, so here that would be a condition where we have no particle. No bueno. Right? Okay, so we don't want that situation. So we're going to stick with always positive, okay, for any interesting situation that we would encounter, which means that in order for, remember, this whole quantity still equals 0, right? So in order for this quantity to equal 0, right, we've already said that the integral of psi star psi d tau is always positive. That must mean that this part of our quantity must be the part that equals 0 to satisfy our equation. Okay, so basically what we've just concluded there is that a minus a star must equal 0, okay, which means that a is equal to a star, right, which is only true if a is real. Right, so remember, a quantity is only equal to its complex conjugate when that quantity is real. So this does not work if we have any complex eigenvalues. Okay, so what this leads us to is the conclusion that our eigenvalues must be real for this situation to hold. Okay, and that is why we like to have Hermitian operators for our quantum mechanical operators. Because remember, when we're doing a quantum mechanical calculation, we are doing a calculation for a measurable quantity. So all of our quantum mechanical operators must relate to a measurable quantity, which means that they must produce real eigenvalues. Okay, so that is why we have that requirement that all of our quantum mechanical operators must be Hermitian. Okay, so if we know we have a Hermitian operator, then we know that we have real eigenvalues, and we also know that this situation up here holds as well for our operators, where our average value of our operator is equal to the complex conjugate of the average value of an operator. Okay, hopefully that helps to clarify things about Hermitian operators, and that will help you in working with some of our examples. Thanks.